Hi, I'm Matt Stahl, and today we'll be talking about biological computers. Biological computers are computers which use synthesized biological components to store and manipulate data analogous to processes in the human body. The result is a small yet faster computer that operates with great accuracy. DNA is the main biological component used in these computers. It was created by Leonard Adleman, a professor at the University of Southern California. His article released in 1994 described how to use DNA to solve a well-known mathematical problem called the Hamilton path problem. Here to talk about more about Adleman's theory is Tim Jacobs. How you doing, Tim?
Good, how are you? It's great to be here, by the way. So, as of right now, you cannot go into a local electronics store and see biological computers. This is because they are fairly new and underdeveloped. A man named Leonard Adleman, like Matt said, discovered this technology by the problem of the Hamilton path problem. Now, this problem was about how to get the shortest route through 7 cities by only going through them once. He used these cities as DNA strands and put them into a tube to see how they would react, giving him a solution to the problem. In his theory, the input of these strands could be a molecular indicator of a disease a person might have. But the problem they are having is constructing a computer to put into the test tube because they cannot control where the interaction will occur with the computer and the DNA molecules. Other problems they are facing is that these DNA strands are not reliable and the molecular operations are not always perfect. But right now, these problems are under research at Harvard, Preston, and the University of Wisconsin.
Thank you, Tim. Now here's Stephen Anderson. He'll be talking about some of the advantages to biological computers. How you doing, Steve?
Doing good. How are you?
I'm good.
Biological computers could be the future in ending cancer. A group of researchers, including ETH Professor Benson and MIT Professor West, made a major breakthrough in cancer research with the biological computers. The computers can actually destroy cancer cells with the network they've created. This computer network is incorporated into human cells and is described as a circuit that determines whether or not a cell is healthy or it's a cancer cell. It contains 5 different cancer factors, and when a cell meets all 5 of those molecular factors, it is destroyed. The network will not destroy the cells unless they meet the required criteria. They have tested the network on human cervical cancer cells, and normal cells. When the computer was introduced to the cells, it only destroyed the cancer cells that weren't healthy.
This is Sam Preston. He'll go into more depth about biological computers as well.
Thank you, Matt. Biological computers are tiny pieces of metal the size of a cell with billions of circuits on them. The way for them to work would be, after they're implanted in your body, it mixes up with your DNA and it helps prevent and cure diseases.
This is Evan Holbert, and he will go into some of the negative aspects of biological computers. How you doing?
Thank you for having me, Matt.
You're welcome.
Since biological computers are recently new in technology, there's going to be a few minor kinks and setbacks during the processes creating them. These setbacks may include finding people willing to have the test performed on them, and also getting legal clearances to have the test enacted, such as putting microchips in people's bodies, as Sam said earlier. When concerned with biological computers, the question of DNA computing arises, because a lot of biological computing has to do with DNA. A DNA computer is a highly parallel computer, which each DNA molecule acting as a separate process or a standard multiprocessor that has a lot of connection buses that transmits each unit to each processor the next. But the problem of transmitting information from one molecule to another in DNA computing has yet to be solved. This is an example of how it's new and how it's probably going to take a few years to get this technology put in order. However, once all the minor kinks are worked out, biological computers will continue to advance and even save many lives in the future.
Thank you, Evan. This is Eric Marino, and he will go into a little more about how the information is stored. How you doing, Eric?
The data is stored in the biological computers is first start out as a binary code, then it's translated into like a protein sequence, and then after that it's synthesized into DNA strands. And after that you can pretty much do anything you want with it, and you could decode it if you ever want to figure out what was on it. And this makes the data storage much larger in capacity, and it's a lot smaller in size. So, like, put it in perspective, it's 1 gram of DNA can store 700 terabytes of data. That's 14,050 gigabyte Blu-ray discs. Then a bioengineer and geneticist at Harvard Weiss Institute has successfully stored 5.5 petabytes of data, around 700 terabytes in a single gram of DNA, smashing the previous DNA data density record by 1,000 times.
Thank you. So that's our presentation and our show. Hopefully that after watching all the interviews, you have a good understanding of what biological computers are. Thank you.